Imagine a problem so vast, so complex. It would take the fastest supercomputer we have today billions of years to solve. This is the scale of some challenges we face, from understanding the deepest secrets of nature to designing life-saving drugs. These problems currently sit beyond our grasp. Now picture a new kind of machine. A machine that doesn't just calculate faster, it thinks differently. It operates on principles that seem to defy common sense. Principles drawn from the bizarre yet fundamental rules of the quantum realm. This machine could take that universe-spanning problem and potentially solve it in mere hours. This isn't science fiction. This is the profound promise of quantum computing. A revolution knocking at the door of reality. Classical computers, for all their power, have fundamental limits. Quantum computers, however, can explore a vast landscape of possibilities simultaneously. We stand on the precipice of a computational renaissance. So what exactly is this quantum computing? At its heart, it's a new way to process information. It harnesses the strange and wonderful phenomena of quantum mechanics. This is the science of the very small, the realm of atoms, electrons, and photons. Down there, the rules of our everyday world break down. Particles can be in multiple places at once. They can be intrinsically linked no matter the distance. This isn't just an academic curiosity. The quantum world is the bedrock of reality. Understanding it and learning to control it opens up unprecedented power. Quantum computing aims to do just that, to build machines that operate according to these subatomic laws. Before we dive deeper into the quantum sea, let's appreciate the shore we're leaving. Classical computers. These are the marvels of engineering that power our modern world. Your smartphone, your laptop, the vast data centers that hum with activity. They all operate on a simple, elegant principle, the principle of the bit. A bit is the fundamental unit of classical information. It can be a 0, or it can be a 1. Think of a light switch. It can be off, representing a 0, or it can be on, representing a 1. This binary system is the language of classical computation. Millions, even billions of these tiny switches called transistors work together. They flip on and off at incredible speeds, performing calculations, storing data, executing the software that runs our lives. This binary logic is powerful. Quantum computers don't just speak a different dialect, they speak an entirely different language. They use qubits instead of bits. A qubit, short for quantum bit, is far more versatile than its classical cousin. While a classical bit is firmly a 0 or a 1, a qubit can be a 0, a 1, or, crucially, a combination of both simultaneously. This mind-bending property is called superposition. It's a fundamental feature of the quantum world. Imagine a coin. A classical bit is like a coin lying flat. Heads, 1, or tails, 0. A qubit is like a coin that is spinning. While it's spinning, it's not definitively heads or tails. It's in a superposition of both states. Only when you stop it, measure it, does it settle into one state. This ability to exist in multiple states at once allows a quantum computer to explore many possibilities in parallel. A huge advantage. Section 5. Peeking inside the quantum engine, how they work. So, how do these quantum computers actually perform their magic? It's a delicate and incredibly sophisticated dance of physics and engineering. Building and controlling qubits is a monumental challenge. Scientists are exploring various physical systems to serve as qubits. These include superconducting circuits, which are tiny loops of metal cooled to near absolute zero. At these temperatures, they exhibit quantum behaviors. Other approaches involve trapped ions. Individual atoms, stripped of an electron, held in place by electromagnetic fields. Lasers are then used to manipulate their quantum states. Photonic quantum computing uses individual particles of light, photons, as qubits. Each approach has its own set of advantages and challenges. The goal is to create qubits that are stable, that can be precisely controlled, and that can interact with each other to perform computations. These quantum systems are extraordinarily fragile. The slightest disturbance from the outside world can destroy their delicate quantum states, a phenomenon known as decoherence. Section 6. Quantum Power Unleashed, Real-World Revolutions. The potential applications of quantum computing are vast. They span across numerous fields, promising transformations we can only begin to imagine. One of the most exciting areas is drug discovery and materials science. Quantum computers could simulate molecules with unprecedented accuracy. This would allow scientists to design new drugs and materials from the ground up. Imagine creating catalysts for clean energy, or superconductors that work at room temperature. Artificial intelligence is another domain poised for a quantum revolution. Quantum machine learning algorithms could analyze complex data sets in new ways. They could train AI models much faster and more efficiently. This could lead to breakthroughs in areas like pattern recognition, natural language processing, and optimization, creating AI that is more powerful, more intuitive, and better at solving complex real-world problems. Cybersecurity is a double-edged sword in the quantum era. Many current encryption methods rely on the difficulty of factoring large numbers, a task that is hard for classical computers, but a sufficiently powerful quantum computer running Shor's algorithm could break these codes easily. This poses a threat to secure communications and data. However, quantum mechanics also offers a solution: quantum cryptography. Section 7. Echoes of the Future, India's Quantum Leap. The quest for quantum supremacy is a global endeavor. Nations around the world recognize the transformative potential of this technology. India, with its rich scientific heritage and burgeoning tech industry, is making significant strides. The Indian government has launched the National Mission on Quantum Technologies and Applications, or NMQTA. This ambitious initiative aims to foster research, development, and innovation in quantum science. A key focus area for India is quantum communication and cryptography. Given the future threat to classical encryption, developing quantum-secure communication channels is vital. Scientists and researchers across Indian institutions are working on quantum key distribution, or QKD. This technology uses the principles of quantum mechanics to create theoretically uncrackable encryption keys, protecting sensitive government, military, and commercial data, ensuring national security in a quantum future. Beyond communication, India is also investing in the development of quantum computing hardware and software. Research groups are exploring various qubit technologies. They are building expertise in quantum algorithms. Fostering a skilled workforce is crucial. Section 8. The Quantum Gauntlet. Challenges on the path to power. Despite the immense promise, the road to widespread, fault-tolerant quantum computing is paved with formidable challenges. We are still in the early days of this technology. Think of the 1940s or 1950s for classical computers. Room-sized machines prone to errors with limited capabilities. That's roughly where we are with quantum computers today. Building these machines is an extraordinary feat of engineering and physics. One of the biggest hurdles is quantum decoherence. Qubits are incredibly sensitive to their environment. Any interaction with the outside world, a stray photon, a tiny vibration, a fluctuation in temperature, can cause them to lose their quantum properties. Their superposition collapses. Their entanglement breaks. This loss of quantumness leads to errors in computation. Scientists are working tirelessly to create more stable qubits and better shielding. Scaling up the number of qubits is another major challenge. While today's quantum processors have tens, or even a few hundreds of qubits, useful applications might require thousands or even millions. Section 9. The universe awaits, a quantum tomorrow. Let's take a breath. We've journeyed from classical bits to quantum qubits. From the familiar logic of on or off to the mind-bending reality of superposition and entanglement. We've seen that classical computers are everyday digital workhorses, think sequentially. Quantum computers, harnessing the bizarre rules of the subatomic world, explore vast possibilities all at once. This is not just an upgrade, it's a fundamental shift in how we can process information. The potential is awe-inspiring, revolutionizing medicine by designing new drugs molecule by molecule, creating new materials with properties we can barely dream of today, supercharging artificial intelligence to solve problems of immense complexity, transforming fields from finance to logistics, even helping us understand the deepest mysteries of the universe itself, from the nature of black holes to the origins of consciousness. The questions we can ask are about to get much bigger. Quantum computing is more than just a new technology, it's a new lens through which to view reality.